Hello everyone. Today I'll be presenting my computer graphics assignment on one of the most important algorithms in the field, the Bresenham's line drawing algorithm. This algorithm is widely used for drawing straight lines on computer screens, and through this presentation I'll explain why it's needed, how it works, and why it's still relevant even today. Here's a quick overview of what I'll be covering. First, we'll understand the problem why drawing a simple line on a pixel based screen is not as easy as it looks. Then we'll look at Bresenham's solution, followed by the simple mathematical idea behind it. After that, I'll walk you through a step by step example to make it more clear. And finally, we will summarize the key learnings. So, the first question is, why is drawing a line difficult for a computer? A computer screen is made up of tiny boxes called pixels, which are discrete, but a mathematical line is continuous. It can pass through any tiny fraction between 2 points. So, whenever we want to draw a line from point A to point B, the computer must decide which exact pixels should be turned on to represent the best possible straight line. The simplest way uses floating point math, but that is slow and inefficient. To solve this problem, we need a faster method that uses only integers. This is where Bresenham's algorithm comes in. It was developed in 1962 by Jake Bresenham at IBM, and it changed computer graphics forever. What makes it special is that it draws lines using only basic operations like addition and subtraction, no heavy floating point calculations. Because of that, it runs extremely fast and gives us a smooth, accurate line with minimal processing. It has three major advantages. First, it's fast, which is important for real time graphics. Second, it's accurate, so the lines look visually straight. And third, it uses a very little memory, making it perfect for hardware like older computers, embedded systems, and even today's GPUs. Now let's discuss about the core concept. The core idea is very simple. As we move from left to right across the screen, the algorithm repeatedly decides whether the next pixel should stay on the same row or move one step up. To make this decision, it keeps track of a value called the decision parameter, which measures how far our plotted pixel is from the ideal mathematical line. With each new pixel, this parameter is updated using a small calculation. Now, the key variables. To draw a line, we need number one, the starting and ending points, denoted by x0, y0 to x1, y1. Second, the differences dx equals to x1 minus x0, dy equals to y1 minus y0, and the decision parameter p equals to 2 dy minus dx. These simple values guide the entire algorithm. Let's discuss the algorithm steps. Here's how the algorithm works very quickly. Number 1. Calculate dx, dy and the initial decision parameter. Then plot the starting point. Then check the value of p. If p is less than 0, we move horizontally. If p is 0 or more than 0, we move diagonally. We'll update p based on the movement. Then we repeat these steps until we reach the final point. The beauty is that this same small process repeats for every pixel, making it very efficient. Let's understand this through an example. We want to draw a line from 2, 2 to 9, 6. We calculate dx equals to 7 and dy equals to 4. Then we compute p equals to 6. Sorry, p equals to 1. Since p is greater than 0, our next pixel becomes 3, 3. Then we update p and repeat the process. By doing these step by step, we eventually reach 9, 6, and the line looks perfectly smooth at pixel level. Bresenham's algorithm is foundational in computer graphics. Even though it was developed more than 60 years ago, the principles behind it are still used in modern graphic pipeline, drawing function, game engines, and CAD software. It shows how powerful simple math can be, even when applied cleverly. Going towards the key takeaways, to summarize, Bresenham's algorithm avoids floating point math, making it super fast. It uses incremental updates, making it efficient for computers, and it remains relevant today because it's simple, elegant, and effective. That's why it's considered a classic algorithm in computer graphics. Thank you. Thanks for listening. I hope you enjoyed. Thank you.